Hello, class. So I will be starting the stream pretty soon. I'm just gonna wait a little bit for people to get here. So if you get here, just check in and yeah. Alright, so let's get started. Okay, so, as you can see from the basic breakdown, we're gonna be, whoops, let me just go back to the start part there. Yeah. Sorry, I was just checking some things on OBS earlier before. But anyway, so, we're just gonna review the properties of exponents and logs, how they work, and then, just practice that stuff. Oh, also graphs. I'm gonna go over transformations again. Okay, so here we have properties of exponents and logarithms. So write these down. You should pretty much already have these down anyway. I literally copy and pasted the code for this from the video that I had you guys watch. Okay, so yeah, if you need to, just take a picture of this real quick. You should already have it anyway, but whatever. In 5 seconds, I will move down and explain stuff that will lead to all of this. Okay, so let's kind of review some basic arithmetic and go from there. Oops, okay, come on. Okay, cool. Okay, so counting. We started counting when we were in elementary school, and how it went was you start with 1, and then you go from there. Each time you go over on the number line, you're just adding 1, right? And then you add 1 again, and you just keep adding 1. And to go the opposite way, instead of adding 1, you subtract 1, and that's what you can do literally every step of the way here. So then that'd be at 0, and then that would be -1. So you can think of this as number of steps of counting by adding 1s. So starting with 1, that's the first thing we got, and then you add 1, that's the second step, which is 2. You add another 1, then you get the third step, which is 3, and so on and so on. Or you go backwards, and you get from 1 to 0 to -1, etc. Okay, so counting by plus a then. We can think of that as multiplication. So let's just start with a, and then if you add another a, you get 2a. If you add another a, you get 3a, and so on, right? And then you can go backwards as well. And get the same type of idea going on. So if we were to do this actually with numbers, then we can think of this as, let's just say, let's use like 10. Then you'll get 10, and then 2 times 10, which is 20, 3 times 10, which is 30, 4 times 10, which is 40. Did I say 40? 40 there, 30, then 40. And going backward, you get minus 10, which is 0, subtracting from there, you get -10, and so on and so on. So this is addition and subtraction, and then dividing, multiplying and dividing. So you can think about dividing as asking basically how many steps it takes to get to a certain place. Okay, so as we go to another way of counting, things got a little bit more interesting in a way. So let's label this as number of steps. So you're multiplying by some value a each time you go over. So in a way, you could have kind of looked at it over here as like, here is your 0 step, your first step, your second step, your third step, your fourth step, and then your -1st step, and etc. And then you just, at the first step, you just have a. At the second step, you add a to get 2a. At the third step, you add a to get 3a. So when you divide, you're actually looking for these numbers here. That idea is going to be very important to understand logarithms and exponents in an intuitive way. So going back down here to logs and exponents. So if we look at these as, actually we can color code this, so I'm going to do that real quick. I'm going to make that yellow and then the other one, I don't know, probably blue or something. That shows up pretty well. So if we have a base, let's just call it A, because we have that. Then we're going to start with A once. And then if we multiply by A, what we end up getting is A squared. And if we multiply by A again, we get A cubed, and this same pattern goes on over and over forever, right? So every time we're going in a positive way, you're multiplying by that base. So that means if you go backward, instead of multiplying by A, you would divide by A. You're doing the inverse operation. So essentially, this is just another way to count. This is counting in a with a multiplying type of way. So if we go backward from A, divide by A, we get 1. Divide by A again, we get 1 over A. And so on and so on. This is why when you have x to the negative n power, you have 1 over x to the n. You're dividing when you do this. You're not getting any negatives in any way, shape, or form. So exponents will never become negative. So just because the power is negative does not mean that the result is going to be negative. Okay, so we can also think about another thing. I'm going to actually put in numbers here to make it a little bit more concrete. Well, after I do a certain thing. Okay, so what if we wanted to actually find out what these were? These yellow things. These are basically all of the step sizes. Like, which step does it take to get a certain number? So basically, if you were counting, so let's just say you're counting in a times A type of way. So we can have a thing called log base A, which tells us we're going to count by multiplying A's. I want A cubed. So what do we need to get there? Well, A cubed. So that would mean that in order to get there, we need the third step. So let's think of it with numbers, and that might help with understanding this a little bit better. So let's just say we have a base of, or multiplier. So your base is kind of like a multiplier. Let's use base 10. That's just easy to work with. So 10, 100, 1,000, 10,000, 1 over 10. Okay, so if we look at it like this, we can ask ourselves the question, if we're going to be counting with a times 10 type of way, then how are we going to get, let's say, 10,000? What is that going to be? So basically, what step do we need in order to get to here? If we look at this, it's pretty clear that that's going to be 4. We can also look at it like this. And I'm just going to do log without the base here, because log without the base means base 10. Let's think about how we can write this as a power. This will be 10 to the 4th. And I'm just going to quickly do a thing that you can do later on as we look through the properties. You can bring the exponent to the front. So for log base 10 of 10, since the bases are the same, this is going to be 1, so we just get 4. Reason for that is So now that we've been kind of talking about these in a certain way, so like, yeah, 10,000 equals 10 to the fourth power. Since we're looking at it like that, it's pretty clear to see that these different components appear in the logarithm as well. So there's a one-to-one mapping of the way that they work. So this one's called exponential form, and this one is called logarithmic form, because exponent and log. So go figure. So we can look at this whole log base 10 of 10 equals 1 thing by thinking, well, the base to the power of what equals 10? If the base and the thing we're trying to get is the same, then it only makes sense that the exponent equals 1, right? So that's why log base 10 of 10 is 1. And up there you saw log base a of a equals 1. Same idea. Okay, so now I'm going to kind of explain a little bit of how this works. If we look at this and we look at this, what that tells us is x multiplied to itself. How many times? 8 times. And then the red part would be x multiplied to itself. It'll be b times. So together, it makes sense then that we get x multiplied to itself, a plus b times. We can apply that same idea to this. So let's make everything to the b power red, and then everything to the a power, or just that little thing to the a power, a. So basically what the red is telling us is x to the a multiplied to itself b times. So that means in total, x multiplied to itself a times b times. So basically what we're seeing here is that there are two different ways that we can work with exponents here. There's multiplying two bases with exponents, and then there's taking something and then raising that whole thing to an exponent. Basically, if you forget these, you can always just kind of logic through, well, what exactly is happening? So with the first one, you can see you have x a times, and you have x b times. Add those, you get them all together, then you get a plus b times. And in here, in the second one, what you're getting is x a times, and then that entire thing b times. So that makes sense then, a times b. Okay, so let's move on to some of the other ones. So, okay, I already explained this one, so in the interest of time, I'm not going to go over it again. I literally just set it up there. This one, I'm just going to take a little bit of time to explain it. I'm going to go back up to the number line. Okay, so now that we're here, we can think of basically if we go half of a step, what happens? So basically what happens when we have something like 1/2? That means you multiply by something. This would be a to the 1/2 power. This would be multiplying again by a to the 1/2 power. So basically, to go 1/2 of the way means that you have to multiply something by itself so that it would get you a to the first power, which would also make sense because you can add those powers together a to the 1/2 times a to the 1/2 equals a to the 1. So basically the question is, what is this? So the 1/2 power itself actually represents square root, because if you have like square root of a times square root of a, that gives you a, right? Or if you have the cube root of a, and you did that 3 times, we can think of that as a to the 1/3 all to the 3rd power. So 1/3, 3 times, and then this is going to be a to the power of 1/3 times 3, which is a to the 1st. So you can think of it as that kind of way. You're like going halfway between two things, or a third of the way, or a fourth of the way, or whatever it is. And that's why these exponents that are fractions are actually a little bit more useful than not. So, all right, let's go back down to properties of logs and briefly talk about these. All right, so here, essentially what's happening is if you add logs of the same base, the insides can multiply. And if you subtract them, they can divide. So I'm just going to do a very quick derivation here, and then we're going to use this for some other stuff right after this. And then I'm running a little bit behind schedule, so going to kind of breeze through some of this. So let's just say, let's let capital A be log base a of x, and capital B be log base a of y. Then we can think about putting these into exponential form. So the base is a, then the exponent is capital A, and then what we're trying to get is x. So similarly, a to the b equals y. Okay, so what if we multiplied x and y together? Then we get xy equals a to the capital A times a to the capital B, which is the same as a to the capital A plus b. And then if we put this into logarithmic form, then we get log base a of what we're trying to get equals a plus b. And a plus b is log base a of x plus log base b a of y. I'm not sure why I wrote either. I'm going to change that. Okay, so it's a very similar thing with this. It's just at some point, instead of doing x over y, you're going to x times y, you're going to do x over y, and then you're going to end up with this, which would be that, and then same exact thing to get this thing. So that's why that works that way. Okay, so now let's look at these two. This one we're going to go over. This one we already went over, so don't worry about that already. We already talked about it. Okay, so log base a of x to the n equals n log base a to the x. What that means, let's think of it like this. Log base a of x times x to the n minus 1. So this is going to be split into addition based on that, right? So essentially, you can think of it like this. You're going to get x times x times x times x times x times x n times. These can all be split up to their own addition. Log base a of x plus log base a of x, all the way forever, log base a of x, until we get this n times. So the easy way to write that is just n times log base a of x. Okay, so that's why that works that way. Now, let's move on to graphing. Okay, so here are the parent graphs of the exponential and logarithmic functions. So we'll graph them together here. So this is y equals a to the x, and y equals log base a of x. Okay, that's a little bit smaller than I thought they were. So I'm going to just write them out and erase that real fast. By erase, I mean just draw over it with black. Okay, so just so that we're on the same page, I'm going to write that y equals a to the x, and then y equals log base a of x. Okay, so let's graph them and make sure that we know what they look like forever, basically. So draw your axis. I'm going to try to make it even, mostly because I'm going to copy and paste this thing to the other one. 1, 2, 3, 4, 5. I'll just copy and paste that here. Or not. Alright, so I'm just going to copy and paste this thing. Oh, wait, I'm going to put numbers and then copy and paste. Because they'll be basically the same kind of thing. Okay, so it'll be important to know some of this information about the graphs. So just like its domain and range and all that. So make sure that you understand those things as you go through this. Alright, so the graph of something to the x power is going to be, I guess you can think of it as, just going to label some of these points actually. So, whoops, sorry. So, always going to have an intercept over here. Always going to have an intercept right there. And then the thing will just grow exponentially this way. And then get closer and closer to the y-axis this way. So you have a horizontal asymptote at y equals 0. And then at x equals 1, you have a point that's going to be 1 comma whatever that a value is. So whatever your base or multiplier, whatever you want to call it, is. Alright. So let's look at the log graph. And what you'll get is something very similar, which would make sense because they're inverses. So at 1 comma 0, you're going to have a point, and then at whatever a is, so let's just say this is a comma 1. And then you'll have the function go basically like that. Just going to redraw those points. Okay, so as you can see, they're basically the same type of thing. If I were to actually put one on the other, you would see that they're very clearly inverses. So now I want to highlight one quick thing before we completely move on. In class, I've been talking about something called reference points, used for used for transformations. And here are the reference points for these two graphs. So given your base a, 1 comma a and a comma 1 are going to be two of the more important points. That'll be for accuracy. You technically could just use the intercepts and the asymptotes. But for accuracy, when you're doing certain transformations, you're going to want to have at least one more point, and those two will give you that point. So I'm just going to actually write over that because this is kind of small. So that's A. I just don't want people thinking that that's 0. And I'm pretty sure some people are going to think that that's 0. Even though I literally said it was A. Alright, so if you need to take a picture of this, please do that real quick. I'll give you 5 seconds, and then I will move on to the next thing, which is going to be practice. And I think right now we'll be actually on time. Alright, moving in 3, 2, 1. Okay, so here's some practice stuff. So what I would like for us to do right now is to take some time to try these on our own. So I'm going to give us about 4 minutes to do this, and then I'll come back and check on these two. Actually, I'll give us 3 minutes. These should be pretty fast by now. I'm just going to give 3 minutes for, like, if you're doing this in 3 minutes, that is a bit on the slower side. And basically that just means you gotta practice more. So I'll give us 3 minutes, then come back, check on this, and then we'll just continue on. Alright, so time's up on that, and yeah, so let's check together. Okay, so for these, you see that you're adding logs, so what you can do is multiply those two together. I know it might be tempting to write x times 3 because of the fact that x is first and then 3, but what I'm actually going to suggest is to do something else. Instead of doing that, just write it as 3x and then equals 2. Always bring that down even though you didn't work on it. Alright, so what can we do with this? Let's turn it into exponential form. So we can do that. And then we need to isolate for x, right? So that just means we can divide by 3. And then x would be 100 over 3, and that's it. So 10 squared is 100. Alright, so 5 times 3 to the a plus 2 equals x times 3 to the a. Alright, so what in the world can we do with this? Well, we want to isolate a, right? So let's just try to get things away from a. Here we have 3 to the a. So let's just divide that out since it's being multiplied. So we get 5 times 3 to the a plus 2 all over 3 to the a equals x. So let's simplify a little bit more. And we'll get x equals 5 times 3 to the a plus 2 minus a, which is 5 times 3 to the... So the a's, they're going to subtract out from each other, right? 3 squared. So we have 5 times 9, which is 45. So even though we had some random little variable looking thing over there, if you actually use the properties of exponents, you'll notice that you actually will be able to cancel this out at some point. Okay, so let's look at this. I want you to write this as one logarithm, so I'm going to give us 2 minutes to do this. This should be fairly quick as well. So think about things. 2 minutes, and I will set a timer for you actually. And yeah. Okay, so I'm going to put that right here. Okay, so beginning the timer now. Alright, so as you can see, the time is up. So putting that away. Okay, so let's go over this and see how it works. So here you're subtracting logarithms, but we can't exactly do that dividing thing yet because there's this pesky little 2. So let's work with that. Well, if you can bring powers down, you can also bring them back, right? So this could be log base 3 of 4 squared minus log base 3 of 5. And now from here, we can divide. So then we have log base 3 of, and I'm just going to do that out and divide in the same step. That'd be 16 over 5. This is written as 1 logarithm. And there we go. All right, so let's look at this. The 1/2, let's not do anything with it yet because we can't exactly. You could technically distribute it, I guess, but I think it's easiest to just work with logs first and then do that later. Okay, so log of 9 plus, so this is going to be also 9 because that 2 can go up. So 3 squared. So basically what we got is 1/2 log of 9 times 9, or 81. And if we do that, then we got log of 81 to the 1/2 power. And actually that would be log of 9, because this is the square root of 81, which is 9. Technically plus or minus 9, but you can't exactly do that here. Okay, so now let's go into the last little thing of practice problems. Graphing, yay. So list all transformations and then graph. So instead of just straight up graphing, I thought it would be better to graph these, just because this is the thing that people tend to need the most help on. Okay, so I'm gonna give us 5 minutes to graph this. You technically should be doing it quicker, but I'm also considering the fact that you're also drawing the axis and everything. So I'll give us 5 minutes on the clock. And yeah, begin. Alright, so now time is up, and let's graph this thing. Okay, so looking at this, we see that we have a few transformations. So there's this first two. This is a vertical scaling by 2. And then we have this horizontal scaling by also 2. A +1, that's going to be a horizontal shift. So it's not just 1, because we also have that 2, right? So this is actually going to be by 1/2 left. And that -4 is going to be a vertical shift 4 down. Okay, so we can look at this as reference points that also go to scaled points and then shifted points. Okay, so the reference points for this are going to be, so I guess we can just write that here, reference. So since it's an exponential, we'll have 0, 1, and then the base is e. So 1, e. And then we have a horizontal asymptote of y equals 0. So with that, if we scale everything vertically by 2, that means we multiply all y values by 2. So that means our horizontal asymptote is going to stay at 0, because 2 times 0 is still 0. And then our 1 is going to be 2, and our e is going to be 2e. Alright, and then our horizontal scaling by 2, so we're going to divide all the x values by 2. 0 divided by 2 is still 0. 1 divided by 2 is 1/2. Okay, so let's look at our shifts. What happens there? So, oops, that's still HA. So, horizontal shift left by 1/2, so that means all the x values you subtract 1/2 from. So 0 minus 1/2 is negative 1/2. 1/2 minus 1/2 is 0. And then vertical shift. Here we're going to get 2 minus 4 is negative 2. And then we get 2e minus 4. I'm going to talk about how to estimate that later. And then horizontal asymptote, that goes down by 4 as well. Alright, so let's start graphing this. I think that's about centered. So knowing that we have our horizontal asymptote down, that means we for sure want to leave some space. Actually, I think that would be a little off center, so I'm going to move that a bit. Unless this graph paper is just off center. Oh well. But anyway, so I'm going to make this a little bit more upward here. Maybe like there. And yeah, let's start putting some of the points in. So we're going to have negative 1/2 and 0 as 2 of the important points. So I'm just going to do every 4 will be 1 for the x's. So I'll be at 1, 2, negative 1, negative 2. And then going downward, let's just do, I guess that works. Oh, also, there's 2e minus 4. E is about 2.71-ish, so 2 times basically 3 is going to be around 6. Minus 4 is around 2. Since it's more than that, it's going to be a little bit above 2, but not by a lot. All right, so that would be negative 1, 2, 3, 4, 5, 6. Okay, so I'm just going to do the asymptote in a different color so that it's easier to see. And then do those important points. So a little bit above 2, and then negative 1/2 comma negative 2. So that would be here. And then we know that this is going to have about the same general shape. So we can kind of just sketch that in. And it'll look something more or less like that. So pay very close attention to the way that I graph this and label it. Alright, so let's move on to the next one. I'm going to give us about 5 minutes to do this one as well. And then we'll check it together. So 5 minutes set on the timer. I will let you see the timer. Doesn't make sense to not let you. Alright, begin. Alright, so as you can see, the time is up, so let's get back to this and let's do it together. Okay, so let's check this. So here we have the logarithm graph, so I'll just put the reference points here real quick. So that'll be x-intercept 1, 0, and then we have another point at a, 1, and then we have the vertical asymptote at x equals 0, and that is the thing that we are going to be transforming. Those are the things, not that is the thing. Okay, so transformations. So we have that negative in front, so that'll be a vertical scaling by -1. So that'll be an interesting thing. I don't like to use the idea of like reflection being different than scaling, just because of the fact that it could get a little bit weird. But instead, I just kind of use them as the same thing, because what's happening mathematically is literally the same thing. So we're multiplying the x's by the y's by -1. All right, so then we have no horizontal scaling, but we have a horizontal shift. One to the left, because we have this plus here. And then we have a vertical shift to up. Okay, so let's look at how this looks. So scaled points, and then shifted points. Okay, so the scaled points, we only have scaling by -1 vertically. So what we will end up getting then is, all we're going to do is take the y values and multiply them by -1. So you may be familiar from different classes that this is a certain type of reflection. And since it's going to make all the y values negative, that's going to reflect over the x-axis. So you can think about it that way too. But the important thing is just multiply all y's by -1. Okay, so 0 times -1 is still 0. 1 times -1 is -1. Alright, we don't scale the x values, so we can just leave them as is. Now we're going to shift. Horizontal shift left by 1, so that means all the x values, you subtract 1 from them, so we get 0, and then a minus 1. Oh, in this case, a is 3. So 3 minus 1 is 2. Wait, did I use a in the previous one too? Hold on, let me check something real fast. Oh yeah, I used the correct number. Sorry. Thought I brain farted. Alright, so, and then vertical shift up by 2, so that means just add 2 to all the y values. So then we end up with these, and then, oh, since we shifted all the x values left by 1, that means same with the horizontal asymptote, so we get this. Or vertical asymptote, sorry. Okay, so let's start drawing the graph. Okay, I think the graph's just not even. Oh well. I'll make the graph paper better later. So let's look at what we're gonna get. So let's see. Important points. We have 1, 0, 3, -1, and then, or 0, 2, 2, 1, and then x equals -1. So I think we can just do it like this, and that'll work out fairly well, just skipping one tick mark each way. Okay. So at 0, 2, we have a point. And then at 2, 1, we also have another point. and at x equals -1, we have a vertical asymptote. If you want to plot a few more points, you can, just for accuracy. But essentially, the curve you're going to get is this. So notice that this should make sense in terms of shape, because we did a vertical scaling by -1. In other words, we reflected the parent graph, which looks like this, over the x-axis, which would make it look like the thing that we actually do have. Alright, so that's this graph. Now let's talk about some applications. So the big question of when are we ever going to see this in real life and stuff like that, let's talk about that. And do some problems related to that as well. And this is going to be the last section. So I'm just going to do some examples of where we would see these and how that actually looks. And then, yeah. Okay, so exponential and logarithmic functions can tell us a lot about certain types of structures. If you have power growth, in other words, there's a multiplier. So if you make something grow through multiplication, that's when exponents and logs are going to be useful. Some common examples would be relative growth and decay. So by relative, what I mean is just like growth and decay relative to some sort of starting point. Which could also refer also then to like interest on loans, interest on money you put into a bank, stuff like that. And earthquake intensity. So actually the magnitude Richter scale is a logarithmic scale. So each time something goes up by 1 magnitude, that's actually times, I think, 10, rather than just like going up by 1. That's why magnitude 6 and magnitude 7, for instance, are very, very different. Okay, so let's just start with some basics. So let's just say we have one bacterium, and every hour, the number of bacteria in this culture triples. So let's write a model that represents this. So let's just say P of t is going to represent the population relative to time. So you start with one bacterium, and then every hour you make it multiply. You multiply by 3, basically. So that could just easily be 1 times 3 to the t power. In other words, just 3 to the t. And that's going to get you what you need. So how long is it going to take for this thing to reach a size of 1,000? This little culture of bacteria. So what is that t? Well, we can turn this into logarithmic form, or you can think of it as applying log to both sides. And then you would get log base 3 of 1,000 equals t. So you can calculate that if you need to or anything. Or you can think of it like this. 3 to the t equals 1,000. You can apply log to both sides. I chose base 10 because then we can do something with this. So we end up with t log of 3 equals log of 10 cubed. So that's going to make it so that we just have 3. So we have t equals 3 over log of 3. So these are actually both the same thing, just in different ways. Okay, so now let's modify the model. So let's say the original amount was 1,000, and there is some sort of antibacterial substance put into the culture such that each hour the population is halved. So P of t, we start with 1,000 and then that gets transformed. How is it transformed is it gets multiplied by 1/2 each hour. So you can think of it like that. But this says write the model in 2 different ways. Well, how can we write it in a different way? Let's turn that into a power. So this is way 1. So let's make this 2 to the -1 power. And we can simplify that even further. And we get 2 to the -t power. So here is the second way to do it. Alright, so then the question is, how long will it take for the antibacterial substance to decimate half of the culture? So that's actually a bit of a trick question. That's just 1 hour, because so this is kind of like, if you think about it, like, how is this going to be 1/2 of 1,000? If t equals 1, then yeah. So what about a fourth? Well, next hour is going to be a fourth, and then so on and so on. So these are just kind of ways that you can think about it. Or you can also look at it as, so 1,000, that's just your starting point, right? The question then is, when is the multiplier going to equal 1/2? So when is 1/2 to the t power gonna equal 1/2? Well, that's when t equals 1. So that works. Okay, so now let's talk about compound interest. Usually you see math teachers go over compound interest talking something about if you're putting money into a bank, and then see what happens with that. But let's talk about student debt now, because that's kind of a real thing. So let's say you have a loan of a sub 0 or a naught. So you can call that a naught. The reason why naught is because that means 0 in the UK, I believe, or some other places. I don't think as much in America. So do that for t years at a rate of r, and that's compounded 9 times per year. So let's put that into some logic. Okay, so we take the original amount, and each time it gets compounded, something happens. So this is going to be a little bit different than the bacteria thing. So let's look at the logic behind this. So we're going to take the original amount, and each time there's compounding, there's going to be something happening. We take the rate, and we divide it into n different pieces. Because if you think about it this way, beginning of the year, end of the year. So the rate happens the entire year, right? There's an annual interest rate. So if it happens n number of times, so this is n, this is 1 through n, then each time the rate is just divided by n, right? So we take the original amount and add n times the original amount. You can think about it as you're distributing this in each time that this happens. And then how are we going to make it so that when t equals 1, then the thing was compounded that many times? Basically, we want this multiplier to happen n times per year. So if t equals 1, then we have to have n multiplied to it as well, because it needs to be compounded n times per year. So that means this multiplier has to happen n times. So you may recognize this as the compound interest formula. And notice that the way that I went about it wasn't just like, hey, here's the formula, here's how, let's just plug things in. But rather, we kind of logicked through it. So we saw with the bacteria, what was happening was I just said the entire culture tripled. Versus now here, we're saying we start with a certain amount, and then each time increment, something happens. And there are 9 of these increments each year. So you're dividing a rate into n pieces, and then you get this multiplier here, which needs to be applied n times per year. So that's how the exponent comes in. Okay, so let's think about it this way then. How long is it going to take to double the money? So I'm going to do this with just variables. This is going to look a bit weird at first, but let's think about what we need to do. So this ain't changing. That's just what you started with. This changes. So basically, when is this going to equal 2. So I'm just going to do it as variables. It's going to look a little bit weird at first, and then we'll kind of interpret some of what's going on. The main reason I'm doing this is actually just to practice with exponents and logs. So when is this going to be 2? Because at some point we want to double that, right? So a0 times 2 is going to give us doubling. So what we can do, let's ln both sides. I use ln just because that's something that you'll actually see quite often in higher level math in college and in calculus. So we get n times t times ln of 1 plus r sub n, r over n equals ln of 2. Okay, so we can divide the ln over, then we get nt equals ln of 2 over ln of that. And then t is just going to be, we divide over the n, ln of 2 divided by n, ln of 1 plus r over n. So this is kind of a formula that tells you kind of what's happening. And so if you wanted to actually know when your loan is going to double in interest, or if you put in a balance to a bank, how much you're going to, how long it's going to take to double, you can actually just plug in the rate and then the number of compounding times, and then you'll see when that happens. All right. So let's go on to something else. Let's actually use numbers here. So let's say that you finish college and you have $37,172 loaned out at a rate of 4.45% compounded daily. So let's modify the model to fit this. So that's a sub 0. 1 plus, okay, the rate is going to be 0.0445 divided, okay, so what is n? If this is compounded daily, then n is going to be 365. So 365 times t. So don't worry about leap years, just to make it simpler, just use 365. I believe normal actual companies and stuff actually use this as well. It just makes things easier, and the one number difference isn't going to actually make a significant difference in terms of money, especially when you're looking at big sums of money. Okay, so what is the balance owed after 1 year? So we can interpret that as, so this represents balance owed. The balance or the amount owed. That's what this represents. So always know what your function is telling you. So if we put that in for a year, then what's going to happen is we get 1 plugged into there. So I'm going to calculate that real fast because nobody can do that in their heads. So you should also be doing this yourself as well. So 37,172 times 1 plus 0.0445 divided by 365, all to the power of 365 times 1, which is 365. And then you will get, okay, so that's 38,863 and dollars and 41 cents. So notice that that's actually quite a big jump from 1 year to the next. It went over 1,000, like pretty close to $2,000. Okay, so a bit scary, but that's life. Okay, so these are going to be the last ones. We're just kind of logicking through things anyway. So, the question is, if you plan to pay this off within 10 years, how much would you have to pay monthly in order to pay it off? So if you want to do an even payment every single month. So let's think. What are we doing to do this? So what we need is to get a total amount, right? So how much is going to be owed after 10 years, and then we can divide that into however many months it's going to be. So think of it as total owed divided by number of months. So that should work. That should make sense. So let's think. Total owed, that's going to be A of 10, right? And then number of months. So if we have 10 years, how many months are in a year? 12. So that's going to be something over 120. So I'm going to plug that into a calculator. Okay, so that's going to be depressing. $63,403.76. So 63,403 and 76 cents. So if we do that and we divide that whole thing by 120, what we get is $528.36 per month. Okay, so yeah, that's how much you'd have to pay monthly in order to pay off something like this. So what if you wanted to pay every day? I don't think that's not realistic. I don't think anything actually allows you to do that. Actually, maybe. Who knows? You can always ask your loan people if you ever do loans for college and whatever. So what if you wanted to pay every day? So you can think of it as total owed. Total owed. I'm going to make that look better. And instead of dividing it by number of months, since we're doing this daily, we're going to do number of days. Okay, so we already know that's $63,403.76 divided by, so I'm just going to assume non-leap years. So 365 times 10. So let's see how that's going to look. Oh, wait. Whoops, I just realized that I plugged something in incorrectly. So, actually the balance after 10 years, I accidentally put 12 in there. $58,000 and $4. 58,004 and 97 cents. Sorry. So some of you probably already saw that that was wrong, but that's okay. We see what we messed up on and we correct it. So then the new monthly payment is going to be $483 and 37 cents. Okay, so sorry about that mistake, but yeah, so we see our mistakes, we fix them, we move on. All right, next thing. So let's see what we're gonna have to owe here. So that'll be 365 times 10, so 365 with a 0 at the end. So you would pay $15.89 actually each day. Okay, that actually looks kind of more reasonable-ish. I mean, it's still the same amount technically, but it's just, if you look at it that way, it could be, you can kind of see it as a bit more reasonable. But anyway, so I actually kind of want to talk about what the thing that I did here specifically. So this is actually from the national statistic. This number specifically is the average um, student loan debt that people have in America, and this is currently the rate for the subsidized federal loan at the time of this recording. And I believe that they're all compounded daily, so that means the interest gets added daily. So, yeah, basically loans are expensive. Usually there's some sort of a payment plan that should be reasonable based on what you have and what you're able to do. So don't be afraid of student loans. I know that it looks kind of scary, the fact that you started with 37,000 and went up to like almost 60,000. Budgeting does kind of help with paying things down, though, and also if you try to pay things off a bit quicker, then the total owed is also going to be a little bit less. You might have a bit higher of a monthly, just based on the way that you do things, but that's one thing that you can kind of think of. You see how scary it is to let interest just accrue for years and years and years. So if you have loans of any sort, best thing that you want to do is to try to see if you can pay things off quicker. The quicker that you do it, the better it is. Also, notice compounding. So compounding daily is definitely going to be a lot more than if you did like compounding monthly, for instance. If you did compounding monthly, actually, let me just calculate that out real quick. If you compounded monthly, then the amount owed after a year it'd still be kind of close. But actually, let's look at what you get after 10 years if it were compounded monthly, because then that's going to show us quite a bit of difference. It'd be 57,958. So that's not a significant amount, but what if we did this like yearly compounding? Then that'd be 57,451. So that is actually a little bit less. What if we did some ridiculous amount? So I just did compounding 10,000 times per year. Then actually it gets to like 58,006 a little bit. So basically there is going to kind of be a limit of what this is going to do, but yeah, there's a lot that goes into these. So you just consider things as you do loans. That's just going to be part of life. People will take loans for any things like college, cars, houses, etc. And now you have some tools to be able to kind of calculate what's going on, what's the best deal, how can you do the best that you can with what you have. Alright, so that's the end of the stream. I think things might have been kind of laggy, so I'm not sure if everything got completely I think the chat's not exactly working anymore because I don't see anything going on in the chat. So I'm guessing that it was lagging for people, and yeah, I'm just gonna cut it off here. And if you have questions, you can email me, send me things on Remind and whatnot. But yeah, so that's the end of the stream. Hopefully it was helpful, and I'll hopefully see you guys next time. Alright, where's the end button? There it is.